Guys, back with another power electronic video. So we're going to be looking at the buck converter. As you can see, it's the simple DC-DC converter, which alongside the boost and the buck boost are the three main DC-DC converters which are taught to undergraduates. And yeah, it's a simple switching circuit, and it allows you to step down the input voltage, and it's quite useful, let's say, compared to a linear regulator like the 7805 or the 7809, something like that. And the difference is that the efficiency of these is much higher compared to those, because the linear regulators just dissipate the extra voltage as heat, whereas in this you vary the duty cycle of this switch here, so you only use how much you need. So that's the beauty of switching circuits. And of course, you to smoothen out the output here, you need the LC filter, which is why you see the L and C. And there's a freewheeling diode. And yeah, you can connect your load here, which in this case is a resistive load. So here, as you can see, the switch here, which is a MOSFET, is on the high side, because if it's between this high input and here, and this is not exactly ground, because only when this switch is on it will supply out the power here, whereas in the other case, when this switch is off, the current through the inductor will continue and the freewheeling diode will provide a path. And in that case, this point would be still around the zero point 0.7 volt above ground, since the drop of this is there. So this is not reference to ground, so you can't directly drive this. You need a high side driver, and in my case I'll be using a bootstrap driver, which I'll show you later. But yeah, this is the basic circuit. And since we're going to be doing open loop, there's this IC. It's a pretty famous one. It's the TL494 TIs, and it's a PWM IC basically. It has many features integrated inside it, and you can even do closed loop with this later, since it has these two error amplifiers. But for now, since we are only doing open loop, we can make use of this DTC pin here, as you can see, which stands for dead time control. But in indirectly we can control the duty with it, even though it's not meant for that directly. We can do that. And the RT and CT here basically decides the frequency at which you want to operate. And yeah, it has two open collector outputs, so we're going to be using one of them. And as I said, since it's a high side switch, we can't directly drive it, and you also need a driver stage in between, right? This can only source and sync up to 200 milliamps, which may not be enough if you are driving a, let's say, a high gate charge MOSFET. So that's where this comes in. This is the IR2110. It's a high and low side driver, or a half bridge driver. And what this allows you to do is basically two functions. It acts as a buffer, and this can source and sync much higher currents. As you can see, it can do up to 2 amps, which is very nice. And another thing is, since what I talked about the high side, this basically uses a capacitor and creates a floating supply, so you can drive the high side. And you can still run this entire IC off a single supply. So if you use something like uh, the TLP or something, TLP 250, which is or TLP 152, which is a optocoupler based driver, there you would need a floating supply, which would increase the number of DC supplies you would need. But in this case, since this creates an artificial supply of sorts, one supply is enough. So we're going to be using this. And yeah, let's just go into the circuit. And yeah, we have the circuit here, the TL494. And as I said, this does have the error amplifiers. So since it's an analog IC, it can pick up noise, so it's definitely better to ground all of them, since we are not concerned with doing closed loop right now. So that's what I've done. And as I said, you can use the DTC pin to control the duty cycle. So I have a 100k pot here. And basically, if you just go through the data sheet, the duty cycle is, the minimum is around 10%, and maximum, yeah, you can go up to 100. And that is basically decided by the amount of voltage which you apply to this DTC pin here. And the IC itself, depending on the supply which you give, which I'm going to be giving 9 volts from a small battery, it generates its own 5 volts. So you can tap into that 5 volts and just add a series resistor to make sure that the maximum voltage here is 3.3, because 0 volts is mapped to roughly 10% duty and 3.3 volts is around 100%. So you don't want the entire 5 volts, so yeah, just add a small series resistor in between, and yeah, the other goes to ground. And RT and CT, which decides the frequency, I'm going to be doing 50 kilohertz, which is a reasonable frequency. Since we're going to be showing this on a breadboard, I don't want to go too high because all the inductances and stray uh, parasitics will start acting up. So 50 kilohertz should be fine. So yeah, based on the formula 1 by RTCT, you can choose this R and C value. And the open collector, there are two, so I'll be using the first one, and just a 470 ohm pull up. And basically the emitter is grounded since it's in the what is it, the standard uh, open emitter configuration. So the output basically goes to the IR2110, as I said. And earlier I used to put this on the breadboard directly, but now I have made a small PCB for it, which I'll show you. So now I'm not going to be wiring this on a breadboard. I have a ready module for this, so that's good. And yeah, I think I've explained this in another video how all of this works, so I won't really get into that. So we have the high side output here, and the floating ground VS, as I said. So now we'll go into the power setup here, and we have the 12 volt input, the MOSFET, the IRFZ44N. So through a 10 ohm, just to limit the, just in case there's any ringing or anything, to limit that, we between the IR2110 output and the MOSFET, we have a 10 ohm there, and you connect the floating ground to the source here. And additionally, we have the freewheeling diode, the L, which the freewheeling I've taken the 1N5819, which is a Schottky diode up to 40 volts. So yeah, it's very fast and low voltage drop. And LC filter, we have 470 microhenry and 47 microfarad. And yeah, this based on the formulas, and depending on how much power you want to draw on the output, you can choose these. And the load is going to be a 33 ohm load. So yeah, it's a reasonable load, not too high. So it shouldn't go into DCM, discontinuous conduction mode, since all the formulas which we use are for CCM, continuous conduction. We want to make sure that it remains in that. So let's add a heavy enough load. 33 ohm seems fine. So yeah, this is the entire circuit here in the open loop configuration. So now let's go to the hardware setup. So yeah, I have the setup here, everything on a breadboard, and preferably you should do this, soldered or something, since this is a switching circuit and power electronics does involve higher currents. But just for POC purposes, this should be fine. And yeah, I have the TL494, as I said, over there. And yeah, we have the 100K pot to vary the duty cycle. And after that, that goes to our IR2110, and as I said, I made a small PCB for that. I etched it myself. So we have it housed over there. That's the IR2110. We have a few bypass capacitors, and yeah, this is the bootstrap capacitor, the bootstrap diode, and just female headers to give the inputs, and screw terminals to take the output. And screw terminals are nice since the peak currents can go a bit high, as you can see, to drive the gate. So screw terminal is better than a female header here. And yeah, try and keep the traces short, since even a small gap increase that inductance. So yeah, we don't want that. And that goes to our output here, which is the power circuit. There's the MOSFET, the 10 ohm gating resistor. There's the inductor. It's quite close to it. It can cause some EMI issues, but yeah, for now it should be fine. There's the freewheeling diode, and that's the capacitor output. And for the load, since it's a power resistor, we can't fit the leads into the breadboard, of course. So I've just used a crocodile cable here, and yeah, it's kept over here. It's the 33 ohm, as I said. It's a 10 watt resistor, so make sure you have a high wattage rated resistor. And yeah, for 9 volt to power the TL494. And the IR2110 and the power circuit itself is from 12 volts from the supply over here. And we view the waveform on the oscilloscope, and we have the voltmeter also to view the output voltage. So yeah, now let me just switch everything on, and yeah, everything is turned on, and as you can see, the supply is on, and we already have the 10% duty, as I said, you can't get 0% duty in the TL494. So yeah, minimum is 10%, and 50 kilohertz. And yeah, we have the 12 volt peak to peak, since it's being driven by the supply itself. And I haven't connected the drain of the, I haven't connected it yet to the output, but yeah, let's just do that first, and we'll see what our 10% duty cycle output looks like. So yeah, let me just connect this. And yeah, now I've connected it here, and you can see we have about 1 volt on the output, and that makes sense since it's a buck converter. And yeah, now we'll vary the pot, and let's increase the duty cycle a bit. You can see how the output voltage varies. So yeah, now we're at about 20% duty, and yeah, we have 2.5 volts. Let's keep increasing it, and now we have 3.3 ish, and let's go to 50%. And yeah, now we're at 50%, and you can see we have about 5.6 volts, and since the supply is what, roughly 12 volts, so we have around 11, if 11 volts minusing all the losses and the diode losses and all of that. Yeah, it seems to be working perfectly. We have around half of the supply voltage here at 50% duty cycle. So let's go a bit further. Let's try and do 70%. And yeah, at 70% we have about 7 volts. And to make sure, you can just touch the resistor, and it is getting a little hot, so you know the power is being, proper power is being drawn. And let's try a little bit more. Let's go to, let's say, 90% duty, and we have very close to the supply voltage. We're at 9.7 volts. And let's say, and in buck it's safe, you can go even up to 100% duty cycle, since your maximum output is just going to be your supply voltage minus the losses. So the on the other hand, for a boost converter, it's very dangerous to go 100% duty, so we try and limit it to maybe 85% or so. But here it shouldn't be a problem. So here now we're at about 95%, and you can see we have 10.3 volts, which, considering we're doing on a breadboard, is very nice. And yeah, now we can even reduce it. Let's go back, and you can see the output is dropping again since I'm decreasing the duty cycle. And yeah, let's go back to the minimum. Yeah, we have 10% duty again as before, and the same 1.1 volt output. And yeah, the resistor is hot, so yeah, you can make sure that it's in CCM by, maybe even we could put a ammeter here and measure the current. But for now, this should be good. And yeah, this was the demonstration of buck converter. And soon I'll be coming up with the boost, and for that we don't need the high side, just a low side driver is enough. So I'll probably switch the IR to, we don't need the IR to 110. But yeah, this was the buck converter demonstration in the open loop mode. So yeah, I hope you learned a little something. And just minus, forgive me for the wiring here, which is messy, but that's how it gets. And yeah, thank you.